A professora Paula.
This call is now being recorded.
Boa tarde, professor Reza.
Boa tarde.
Boa tarde.
Todos estão me ouvindo bem?
Sim.
Aqui também.
Bom, então vamos dar continuidade aqui, né, à programação do workshop. Aos que não me conhecem, eu sou Francisca.
Só um minuto, pode esperar um minuto para chegar o horário?
Posso sim.
Tem um monte de gente que ainda vai entrar, né? Tem muito pouca gente.
Eu estava esperando. O meu, professor?
Não, acho que ele Fran.
Oi?
Tá com retorno.
Bom, eu já desativei tudo aqui. Só um momento. Melhorou agora a questão do retorno?
Sim, a ver, sim, agora sim, agora, pronto, agora tá ok.
Pronto, eu tirei aqui uns equipamentos que estavam no quarto. Posso começar, professor Reza?
Sim.
Vai querer começar já, Reza? Vai esperar um pouquinho.
Eu acho que já é hora, né? Para a gente não atrasar, é bom começar já logo.
Bom, então, vamos retomar aqui a programação do workshop, né? Inicialmente, em nome da comissão organizadora, eu agradeço a presença da professora Paula Caregnato, né, em contribuir com esse nosso momento de divulgação científica. Bom, fazendo aqui a apresentação da professora Paula. A professora Paula, ela é pesquisadora na Universidade de La Plata, e desenvolve estudos envolvendo a reatividade de diferentes radicais inorgânicos de interesse ambiental, desenvolvimento de pontos quânticos de silício luminescente, também trabalha com a obtenção de nanocompostos luminescentes e magnéticos de partículas porosas de sílio e magnetita, nanocompostos baseados em hidroxiapatita para remoção de íons metálicos, e também de sistemas de ZNO dopados para remoção de contaminantes orgânicos via fotocatálise. Então, eu vou passar aqui a palavra para a professora Paula, e após a apresentação dela, se algum aluno, algum participante tiver interesse de fazer alguma colocação, é só colocar aqui no chat ou levantar aqui a mãozinha, tá bom?
Good afternoon. I'm going to share my presentation. Okay. Oh, I don't know why it isn't appearing. Sorry. Okay. My presentation doesn't appear. I'm sorry. Here. Okay, good afternoon. Thank you for the introduction and the presentation. Thanks to the organizing committee for inviting me to be a speaker in this workshop, mainly to Francisca, who contacted me to be a speaker here. Okay, I'm from La Plata, Argentina. It's a city that it's named, it's called the City of the Diagonals. You can see here in this picture that there are not only perpendicular streets, but also many diagonals all over the city. My workplace is in IFTA, that depends of CONICET and University of La Plata. Okay, let's start with science after my short introduction. The pollution of water, air, and soil has an impact in the quality of life. Concerning pollution in water, the study of emerging contaminants has become an important topic in environmental research. Emerging contaminants are a group of natural and synthetic substances and its transformation products. The main characteristics of the emerging contaminants are that they are present in trace concentrations in water bodies from microgram to nanogram per liter. There are absence of treatment protocols and monitoring, and the minimal knowledge about ecotoxicological impacts on aquatic life and human health. The emerging contaminants are categorized into classes. One of them are pharmaceuticals, which includes prescription drugs and drugs of abuse. Carbamazepine is an antiepileptic drug. It is highly persistent and resistant to biodegradation. In the last few years, many papers have reported that because of the different anthropogenic activities, many pharmaceuticals, such as carbamazepine, have appeared in different water bodies in Argentina. Here I have shared some papers in the Misiones province, here in the northeast of Argentina, in Acaragua and Paraná River. It was found bioaccumulation of carbamazepine in 3 tissues of 4 fish species. In addition, in Talamuchita River Basin, here in the central Argentinian region, carbamazepine was found in high levels. And in the La Plata River Basin, carbamazepine was found in the muscle of 4 fish species in high levels and among other pharmaceuticals. So we conclude that conventional methods of water treatment exhibit limitations on the removal of that kind of emerging contaminants. So there is an urgent action to analyze and remediate such compounds in water. The advanced oxidation processes are an alternative to this to the treatment of water. They can be used as pre-treatment or as a post-treatment. Here, I'm sharing some of the advanced oxidation processes. I'm going to talk about photocatalysis. Photocatalysis needs a solid semiconductor. According to band theory of solids, the semiconductor, there is a band gap energy between the valence and the conduction band. And when the semiconductor is irradiated with an energy light of higher than the band gap, a pair, an exciton is formed. It is electron-hole pair. Zinc oxide is solid semiconductor with a band gap energy of 3.2 electron volts. Besides, it's a material of low toxicity, low cost, and presents a wide band gap. It means that when the zinc oxide absorbs radiation below 100 nanometers, an exciton is generated. There are several mechanisms of photoactivity in all the semiconductors. First of all, there are direct processes. In these processes, the substrate that can be an organic molecule or contaminant, organic contaminant, the electron of the conduction band and or the hole in the valence band react with by a reduction or an oxidation reaction with the substrate. In addition, we have the generation of free radicals when the electron in the conduction band reacts with adsorbed oxygen, triplet oxygen. It is generated superoxide radical anions, and when the hole reacts with water, hydroxyl radicals are generated. Those radicals are able to react with the substrate. Looking at the standard reduction potentials of these radicals, the hydroxyl radical, we can see it is a powerful oxidant. Besides, it is highly reactive, presents short life, and is non-selective. Another mechanism of photoactivity is the electron-hole recombination. It is a disadvantage when this semiconductor wants to be used in photocatalysis because of the loss of charged carriers. If the electron and the hole recombines, they are not no more available to be present in direct processes or in the generation of free radicals. So the zinc oxide semiconductor presents many disadvantages. One of them is that I have mentioned before, and the others are the inefficient absorption of visible light and the photocorrosion. Those disadvantages decrease the photocatalytic activity of the material, which can be sort out modifying the solid with metals such as cerium. So the general objective of the work I'm going to present is the design of photocatalysts based on zinc oxide for the degradation of an emerging contaminant. There are many ways of synthesized the zinc oxide materials. I'm going to show you the three we performed in our lab. The first is the Sol-Gel synthesis. The other is the microwave-assisted Sol-Gel synthesis. And the last one is the zinc oxide obtained from spent alkaline batteries. In the Sol-Gel synthesis, the precursor is the zinc acetate, and the sol is generated adding an ethanolic solution of oxalic acid with stirring and heating during an hour. The wet gel is generated after 24 hours, and then the gel is separated by centrifugation. It is dried and finally calcined at 500 centigrades. This material is named zinc oxide Sol-Gel. The same material was, by the same synthesis way, mechanism, it was modified with cerium. It was used cerium nitrate with a quantity of 5 nominal atomic percent, and the salt was generated by adding the ethanolic solution of oxalic acid. The following steps are the same that in the synthesis of the material without cerium. This new material is named 5-cerium zinc oxide acid because it was obtained in acid media. Another material obtained by salt gel synthesis is the following. The same precursors were used: zinc acetate, cerium nitrate, and the solid was generated by adding dropwise an ethanolic solution of sodium hydroxide until the pH of the reaction mixture was equal to 8. The following steps to obtain the solid were the same than before. This material is named 5-cerium zinc oxide basic because of the basic media. The second group of catalysts that were obtained by microwave-assisted salt gel synthesis are the precursor were the zinc acetate. The salt was generated by adding the oxalic acid ethanolic solution, stirring and heating during 10 minutes, and the gel was obtained in a microwave digester system with temperature in a total time of 30 minutes. The gel was separated by decantation, and the solid was dried and calcined at 500 centigrades. The solid is named zinc oxide microwave. The same the cerium modified zinc oxide by microwave-assisted salt gel synthesis was obtained incorporating to the precursors cerium nitrate, but now in a quantity of 0.5 nominal atomic percentage. The following steps were the same than the procedure without cerium. The material here is named 0.5 cerium zinc oxide microwave. The advantages of this synthesis were the lower synthesis time and the simple separation of the gel. And finally, the zinc oxide obtained from spent alkaline batteries. These batteries were dismantled and separated, and the anodic paste was kept. This anodic paste was treated with sulfuric acid and with hydrochloride acid. The solid was precipitated with potassium hydroxide and finally calcined at 400 centigrades. Two materials were obtained. One is zinc oxide from sulfuric acid, and the other is the zinc oxide from hydrochloride acid. The advantages of this method of methods of obtain this solid are the recycling of zinc and the environmental and economic benefits of giving value to a waste. Okay, we have made lots of characterization of all the materials. I'm going to show you just some of them. Raman, I'm showing you all the Raman spectra with the 3 different methods of synthesis. All of the zinc oxide materials have the peak of Wurtzite phase characteristic of zinc oxide, except the except the 5-cerium zinc oxide acid. All the materials that were modified with cerium presented a second fluoride cubic structure characteristic of cerium dioxide. These are some images of the scanning electron microscopy of the 3 materials obtained by Solgel method. We can see by SEM microscopy the morphology of the solids. All of them are present spherical particles, and we can see that the average particle size decreases with the cerium content. By EDS analysis, the cerium content were calculated. For this material, it was 3.4 atomic percent, and for this other material, it was 0.4 atomic percent. Here are the scanning electron microscopy of the materials obtained by microwave synthesis. We can see that the one without cerium are spherical particles which agglomerate, forming rods, and the catalyst that contain cerium, we see spherical particles that were deposited on a plate-like morphology. The average particle size was measured, and we can see also that with cerium content, the average particle size decreased. By EDS analysis, the cerium content was 0.2 atomic percent. Here, I'm going to show you an image obtained by TEM microscopy, by transmission electron microscopy. It is an EDS mapping profile. And we can see big spherical particles with size of around 50 nanometers, and the EDS spectra of these particles show that the presence of zinc and a small quantity of cerium. Besides, we have small particles that are here in green color. They are particles of 5 nanometers size, and the spectra of each particle by EDS show the presence of cerium and not zinc. So we have zinc oxide big particles which are surrounded by smaller particles of cerium oxide. In the I'm I'm not sure that I say that this TEM image is of this material, 5-cerium zinc oxide basic. For the zinc oxide, for 5-cerium zinc oxide acidic, the EDS mapping profile in TEM microscopy is quite similar to the one I showed before. We have big particles of zinc oxide and smaller particles of cerium oxide, which were surrounded and in some cases forming agglomerates in the sample. Okay, here are two 10 electron microscopy of the materials obtained by spent alkaline batteries. We can see here the zinc oxide obtained by hydrogen chloride. They are very small compared with the ones obtained by sulfuric acid. Okay, let's start with the photolysis experiments. For photolysis, we used a Rationette commercial reactor. A cylindrical glass reactor was placed in the center. Inside this glass reactor, the reaction mixture of the contaminant, carbamazepine, and each catalyst were placed. Surrounding the cylindrical glass reactor, the lamps were fixed. We used UV lamps or visible lamps. Here I showed you the spectral irradiance of the UV lamps. It is the red line. We can see that it has an emission maximum in 365 nanometers, and the spectrum of the visible emission spectrum of the visible lamp presents several peaks with a maximum in 575 nanometers. The quantification of carbamazepine at the different irradiation times was performed with an HPLC equipment with absorbance detection. Okay, here I'm showing you the absorbance spectra of the contaminant, the carbamazepine, and the reflectance spectra of some of the solids, of some of the catalyst. As we can see in the spectral irradiance of the lamps, the light was only absorbed by the catalyst. Okay, let's see our results. 2 control experiments were performed, one without light, just the carbamazepine and the catalyst, and the other without the catalyst, just the carbamazepine and the light. After 3 hours of these control experiments, the concentration of carbamazepine decreased less than 10%. I'm going to show you first all the results with the catalyst obtained by salt-health synthesis. Here in this figure is the percentage degradation of carbamazepine with each catalyst. And the result, we are going to discuss, first of all, the difference between the 2 materials which were modified with cerium. They present the surface to volume. We are going to discuss the surface to volume ratio, the cerium content, and the crystallinity. As we have seen in the characterization techniques, the cerium modified zinc oxide is obtained in basic media, showed a smaller particle size, a small quantity of cerium, 0.4 atomic percent, and it was crystalline. After that, we made an experiment using a 475 nanometer cut-on glass filter. So the emission that reached the material, I mean the catalyst, was up this wavelength. With these filters, the percentage degradation of carbamazepine changed drastically. We can see here with the results with the presence of the filter, and the other is without the filter. We have seen before that results. So the cerium modified catalyst shows a slightly improvement in the photocatalytic activity with respect to the zinc oxide without cerium, with the irradiation source higher than 475 nanometers. We proposed a mechanism according to bibliography. The mechanism proposed was that cerium acts as an electron trap to inhibit the photogenerated electron-hole pair recombination. Okay, we have seen before that one of the disadvantages of cerium oxide was photocorrosion. It means that metal leaching from the catalyst occurs. We can see here in the reaction how is photocorrosion. I mean, the solid zinc oxide reacts with the photogenerated holes and produce zinc cations. These zinc cations are source of water contaminations, and this process has a negative impact in the reuse of the catalyst. So we study the cerium effect in photocorrosion. We measured the quantity of zinc in the aqueous solution after the 3 hours of photocatalyst. We can see in our results that the content of cerium decreased when photocatalyst was performed with cerium-modified solids. So we proposed that the cerium oxide, small nanoparticles that were surrounding and were distributed superficially around the zinc oxide could be an impediment for the diffusion of the zinc cations to the solution. In addition, we studied the pH effect in photocorrosion. In bibliography, we have found that the slowest dissolution occurs at pH of 10. So we developed a photocatalysis changing the pH of the reaction mixture, adding sodium hydroxide until the pH was 10. And we can see that after the 3 hours of photocatalysis, the quantity of zinc decreased, and its value is close to the quality parameter of the permissible discharge limit. Besides, we can see that at the pH of 10, there is an improvement in the catalytic, photocatalytic activity of this material. At pH of 10, there are large number of hydroxyl ions in solution, and the catalyst surface is highly hydroxylated. So both effects facilitate the photogeneration of more hydroxyl radicals. Okay, I'm going to show you now our photolysis results with the materials obtained with microwave-assisted Sol-Gel synthesis. With 8 visible lamps, here we can see the percentage of degradation of carbamazepine with both catalysts. We studied after 3 hours. She is always after 3 hours of photolysis. We studied the Sirium effect in photocorrosion. We can see here in the table that the amount of zinc in aqueous solution after the photocatalysis is decreased. Besides, we studied the pH effect. Here in this experiment, we adjust the pH of the reaction mixture to 7 by adding sodium hydroxide. And at this pH, we found that the amount of zinc in the aqueous solution after the photocatalysis has a value, again, that is very near to the quality parameter of the permissible discharge limit. The carbamazepine percentage degradation at this pH with this photocatalyst, we can see an improvement. We are not only decreasing the photocorrosion, but also having a better performance for the degradation of the contaminant. And we also use a total organic carbon analyzer to measure the mineralization of carbamazepine. Always after 3 hours of photolysis. Our results are here for each photocatalyst, and we can see that the percentage of mineralization is low in both cases. So we proposed a mechanism according to bibliography. How is the reaction of the radicals generated by photocatalysis and the contaminant? We proposed that the hydroxyl radicals, the addition of them to the carbamazepine and further intramolecular reorganization yield product with similar carbon content than carbamazepine. So as the mineralization has is low, we we analyzed the toxicity of the products and intermediates after the 3 hours of photolysis. For that, growth inhibition tests were performed with 2 different bacteria. These were the bacteria we used. And the streptomycin was used as a reference substance, and the growth inhibition of each bacteria was tested. We can see that for this catalyst, before and after the 3 hours of photolysis, no growth inhibition was found. The same with the 0.5 serum-modified catalyst. So we can conclude that there are no differences in the toxicity of the reaction mix before and after the photocatalyst using this bacteria. Okay, and finally, these are the results of photolysis with the zinc oxide obtained from spent alkaline batteries. Using the visible lamps, we can see that the percentage degradation of the contaminant is very, very low. They are inside the error. But with the UV lamps, the UVA lamps, the percentage of degradation of carbamazepine with both materials is quite good. So our further work is used for all the photolysis or the one catalyst that have shown better performance, solar radiation. It means sun exposure or simulated solar radiation. And in future, we are going to try to design new photocatalysts. It means heterostructures of zinc oxide nanoparticles and titania nanobelts with the incorporation of iron oxides in order that the material are magnetic and can be separated easily from the reaction mixture with external magnetic field. This is the work group. Here it's me. Paula Villabrille is my partner. She works at Sindeca here in La Plata. Carol was a student who worked with the synthesis and characterization and the photocatalysis experiment with the Sol-Gel materials obtained by Sol-Gel method. Victoria Gallegos is a researcher at Sindeca. She obtained all the material from the spent alkaline batteries. Here is the project that have financed our research. And to say goodbye, I'm going to show you some pictures of La Plata City to know my place. Of course, all are invited to come and visit me, to visit and know INIFTA, and of course, collaborations. Obrigado por sua atenção.
Graças, professora Paula. Alguém tem alguma colocação a fazer? Alguma pergunta? Alguma dúvida?
Buenas tardes, profesora, ¿todo bien?
Buenas tardes.
Vamos a mezclar un poco las lenguas. Aquí es bueno para descontraer un poco.
Sí, sí.
Yo quería apenas saber, el método de Sol-Gel es un método muy bueno, ¿no? Para sintetizar materiales. Más una cosa que pasó mucho en algunas pruebas que hice en algún momento es que era difícil llegar al punto gel, ¿no? Partiendo de esos nitratos, porque siempre que colocaba la base, pasaba que comenzaba el proceso de precipitación de la solución.
Sí.
¿Cómo ustedes consiguen controlar, así llegar al punto gel mismo, tener aquella parte de gel final sin que el nitrato, el acetato en este caso, precipite?
Sí, es como vos decís, es difícil porque aparece, o sea, es una competencia entre la formación del gel por método Sol-Gel y la precipitación, ¿sí? En realidad lo que hicimos fue trabajar, o sea, el proceso Sol-Gel, tal cual lo mostré, es un proceso lento, o sea, son varias etapas y cada etapa hay que trabajar en agitación, en temperatura, y tiene su tiempo. Creo que ahí fue donde hicimos como el hincapié para trabajo en detalle, como para llegar a obtener el gel por el método Sol-Gel. Además, creo que fuimos exitosos porque el tamaño de la partícula es pequeño. Siempre que es precipitación, los tamaños son mucho más grandes, hay más aglomeraciones y de acuerdo a nuestras caracterizaciones hemos obtenido, creo que un buen gel, ¿sí? Pero no sé si respondo bien tu pregunta, pero me parece que el éxito es que cada etapa tenga su tiempo, ¿no? Como hemos hecho. No sé, ¿ustedes han trabajado con óxido de zinc también?
Sí. Hemos trabajado bastante con óxido de zinc, dopado, inclusive dopado, codopado también, mezclando tanto tierras raras como metales de transición, hierro, cobalto, níquel, cromo, estroncio, y pasaba mucho eso, ¿saben? Inclusive nosotros usábamos ácido cítrico, ¿no? Para ayudar en el proceso de gelificación, de llegar al punto gel, y conseguíamos. Más en algún momento percibíamos que trataba de la solución precipitar, ¿no? Solo que como que conseguía otra vez estabilizar nuevamente junto con el ácido cítrico, quedar en aquel punto gel, ¿no? Más es muy complicado, es bien complicado.
Sí, es complicado, sí. Es así como vos decís.
Muchas gracias y felicidades por la presentación.
Gracias.
Mais alguém tem alguma consideração a fazer? Bom, eu queria saber da professora Paula, né? Agradecer aqui, né, a apresentação dela. Eu já a conheço da época da defesa, né? A gente trabalha também com ZNO. Eu queria saber se a professora fez testes usando outros percentuais de dopantes.
Otros dopantes
percentuais diferentes.
Otros dopantes distintos del serio.
Sim, e se vocês chegaram a variar o percentual desses dopantes comparando com a atividade fotocatalítica.
Otros dopantes diferentes del serio no hemos probado. No hemos probado. Comenzamos a trabajar con serio, dopando con serio, porque Paula Villabrille, que es una de las del grupo de trabajo, había trabajado con dióxido de titanio dopado con serio y había obtenido buenos resultados. Entonces, ese fue nuestro punto de partida para usar ese dopante. No hemos utilizado por ahora otro dopante. La idea, digamos, usar otro, no sé si nuestro futuro trabajo va a ser usar otro dopante. sino trabajar mejor con heteroestructuras, ¿sí? Como mencioné al final. Ahí apunta nuestro trabajo a futuro. Creo que las heteroestructuras como fotocatalizadores son mejor, digamos, hay más para explorar que los dopantes. De dopantes hay mucho trabajo hecho hasta el momento. Sigue habiendo.
Entendi, professora. E é mais agora uma curiosidade. Eu vi que vocês testaram, né, a toxicidade dos fotoprodutos ou dos intermediários utilizando cepas de bactérias. Aí eu gostaria de saber o que foi que motivou o grupo a testar com bactérias. Vocês consideraram que estavam absorvidos? Como foi?
No, fue digamos, ese trabajo lo hicimos en colaboración, no lo hicimos acá en el INIFTA porque en el INIFTA no hay infraestructura para trabajar con bacterias. Entonces, fue una colaboración con una gente que estudiaba toxicidad. En realidad, trabajan este grupo con el cual hicimos una colaboración. Trabajan con toxicidad de pinturas. Y bueno, y vimos la posibilidad de usar esas bacterias para evaluar la toxicidad de estos materiales. Perdón, materiales no. La toxicidad del contaminante y comparándola con los productos que se forman. Como hay poca mineralización, en otro producto orgánico se está transformando la carbamazepina. Entonces, las bacterias con las cuales se hicieron esos ensayos de toxicidad fueron realizados por colaboración. Eran las que estaban utilizando el outro grupo de trabalho.
Não, eu achei muito interessante, professora, porque a gente trabalha, mas a partir de uma outra perspectiva, e eu não tinha visto ainda. Eu achei bem interessante. Bom, se alguém tiver alguma pergunta para deixar no chat ou quiser fazer pessoalmente, por favor, se manifeste.
Eu vou aproveitar, então. Na
Oi,
verdade,
Mayara.
eu tenho uma curiosidade. Olá, professora Paula, parabéns pelo trabalho, pela pesquisa. Posso fazer em português mesmo? Ou...
Sim, sim.
Espanhol não consigo, inglês dá para tentar.
Não é problema.
Mas é a curiosidade sobre o contaminante, porque até peço desculpa que eu perdi os primeiros slides, eu queria entender o contexto, a motivação. Esse tipo de contaminante, se eu não me engano, eu vi o nome, ele é carbecitina, uma coisa assim?
Carbamazepina.
Carbamacetina, isso.
Sim.
De onde vem, assim, é um tipo de fármaco, de subprodutos de fármaco ou de indústria, de outro tipo de indústria? Como é? De onde vem esse poluente?
¿Cómo llega a los cursos de agua? ¿La pregunta?
A produção dele, assim, ele é um subproduto de que tipo de geração, de indústria, enfim?
No entiendo la pregunta. Es
porque ella la
carbamazepina.
Carbamazepina es
un fármaco.
No es un fármaco, Mayara. No, él no es un residuo o como los colorantes, como los, ¿sabes? Él es un fármaco, es un medicamento.
Entendi.
Claro.
Él no va a ser un residuo de ni un producto de industria.
Yo entiendo. Claro, lo que pasa es que aparece en las aguas. Eso es porque por los descartes hogareños, por los descartes en la industria farmacéutica, o sea, llega a los cursos de agua por la actividad antropogénica, ¿sí? O sea, la actividad del hombre hace que, como hay cada vez mayor consumo de fármacos diferentes, hay más residuos.
Sí.
Y bueno, como no están regulados, o sea, no hay tratamientos para eliminarlos.
Sim, tá certo. Então ele é produto farmacêutico. Era essa curiosidade.
Sí. Está bien, está bien, está bien.
Obrigada.
Gracias, Mayara.
Mayara trabaja con nosotros aquí también y junto con Fran.
Ajá.
Y recientemente hicimos un trabajo sobre óxido de zinc exactamente, con cerio y níquel.
Ajá. Mira.
Y fotocatálisis que fue realizada en Teresina, allá en Piauí con Fran. Y
perfecto.
por eso es que ella está interesada en el tema, ¿no?
Claro.
Una buena pregunta, Mayara, porque no solo estos colorantes, ¿no? Estos que se usan, sino ya puedes ver que los estudios de fotocatálisis puedes hacerlos en fármacos, ¿no? Que también, como la profesora mencionó, yo sé, en las casas, en las industrias farmacéuticas existe todo ese residuo, ¿no?
Sí, hay muchos fármacos que aparecen como contaminantes emergentes, ¿no? La carbamazepina es uno de ellos, pero hay otros. Nosotros ahora vamos a estudiar otros que son atenolol, también la cafeína, que no es un fármaco, ¿no? Pero sin embargo también aparece constantemente en los cursos de agua y en mucha cantidad. Entonces termina siendo un contaminante emergente.
Y son más difíciles de degradar.
Sí,
son más difíciles que los colorantes, ¿no?
Sí, por la misma estructura orgánica que presentan, sí. Ustedes han trabajado siempre con colorantes, o sea, ¿han probado los fotocatalizadores para la degradación de colorantes?
Sí, hasta ahora sí. Estamos haciendo unas pruebas con CNO también, con tierras raras, con algunos fármacos también. No me acuerdo, Fran, ¿cuál es el nombre?
Com
no me acuerdo.
ibuprofeno, a gente tem teste com ibuprofeno
Ibuprofeno.
e com paracetamol, né? São os dois fármacos que nós testamos. Não, paracetamol não. É com um antibiótico. Eu não lembro agora o nome. Mas a gente está testando com antibióticos.
Sí, antibióticos también.
Isso, são os poluentes emergentes.
Sí, los antibióticos y los metabolitos de los antibióticos también están presentes en los cursos de agua. Bueno, podemos trabajar juntos entonces. Vamos a...
sí.
Claro, yo creo que sí.
Sí.
Las preguntas son exactamente por eso.
Sí, por supuesto. Sí.
Eu tenho mais uma pergunta.
Sí.
Para aproveitar o tempo, né? Ainda está sobrando.
No hay problema.
Eu vi nos slides sobre prospecções futuras que vocês vão testar com exposição solar ou simulação parecida. Vocês já fizeram esse teste em exposição solar com outra pesquisa com fotocatálise?
Yo no, pero Paula Villabrille, que es mi compañera de trabajo, sí, ella ha realizado estudios con exposición solar natural, luz solar simulada, con dióxido de titanio. Tiene algunos trabajos con esse tipo de radiação, sim.
Agora, eu tenho uma curiosidade, Mayara.
Fala.
Professora Paula, sobre essa exposição, sobre esses trabalhos utilizando luz solar natural, né? Como que vocês fariam controle de algum outro parâmetro de temperatura?
Sí, hay que hacer ciertas medidas con un radiómetro, o sea, hay que medir, tiene que ser determinado horario, tiene que haber, no tiene que estar nublado, por ejemplo, o sea, hay ciertos parámetros que para ser comparable, ¿no? O para que lo acepten como publicación, tiene que haber ciertos parámetros y ciertas medidas, ¿sí? Se mide con un radiómetro, se mide la radiación, ¿sí? En un intervalo, ¿sí? Del espectro de longitudes de onda, y bueno, se puede trabajar, sí. Acá se han hecho en La Plata, en general se hacen en verano, primavera, o sea, depende, ¿no? mucho de la zona, ¿sí? El resultado.
Mas é bem interessante, né? Porque se aproxima bem de uma aplicação, né, real em termos de escala, em termos de indústria, né? Bem interessante mesmo. Sim. Mais alguém tem alguma colocação? Bom, Eu acho que ninguém tem mais, né, nenhuma pergunta a fazer, então, em português mesmo, eu vou agradecer à professora Paula, né? Muito obrigada, professora.
No,
por
muchas
aceitar.
gracias a ustedes por la invitación, un gusto participar. Lástima que no puede ser presencial, ¿no? Si conversaríamos más tiempo.
Com certeza, com certeza. Até porque eu não lhe conheço pessoalmente. Da vez que você veio para o workshop, eu não participei, né? E a minha banca, no caso, foi online. Né?
Sí,
Mas, de toda
online.
forma, tenho muita vontade de conhecê-la também pessoalmente, né? Para a gente trocar
Sí.
figurinhas de foto catálico.
Sí.
Muito obrigada, professora, pela apresentação, pelo seu trabalho aqui, que foi, né, a sua linha de pesquisa, que foi mostrada, demonstrada para todos nós, e pela contribuição aqui, né, acadêmica na formação de outros profissionais, e também, né, agregar mais informações às linhas de pesquisa de outros professores pesquisadores. Então, muito obrigada, tá? Vamos dar continuidade ao workshop. Queria chamar o professor Reza, ou o